forget. A lot of questions about, not a lot, but a couple, about the homework or assignment. So question 1 is just a general ODE, right? It's a second order system. You have to convert it to first order system. So change of variable and do that. If you don't remember, just Google change of variable, second order system to first order. You see a lot of examples. That's just basically to walk you through how to do it. And in question 2, you can use it, right? Because question 2, you have the equations in the book and in the lecture. You basically can use that. The help that I've given to some of the students is that, do you remember when we started talking about dynamics, robot dynamic? We said there are 2 kinds of problems: forward dynamic, inverse dynamic. You need to figure out which one is this question, and then go and check that slide and rearrange the equations. Then you'll be fine. All right. Today, we will run this code if I get there. If not, it doesn't matter. This is single link robot and robot. And so basically the first part of your problem is solved. So in homework 4 question 2, you have 2 link robots, right? This is 1 link. So if you go through this and see how it is solved, you should be able to translate it to 2 links. What is different? The dynamic equation. It's just more equation. It has a PD controller in it. And for your CP that is due on Monday, you have to tune the PD controller. So the code is written, you have to manipulate the numbers. Just going through and see like how it is. You can just give like big random number to see how it impacts your system, so you understand how controller works, right? But for the CP, you have a certain requirement. Okay, so take advantage of this for your work. And then this is a link for a 6-degree freedom robot, and you'll see that like once you learn 1, 2 links, when you learn how to apply the controller, it doesn't matter how many links the robot has. You can use the same concept for that. So hopefully this course will set you up for, if you wanted to continue in robotics, you know, in more advanced classes, whatever is after this, if you're taking it, what are they talking about? They're talking about robotics. All right, so this was just, course is mostly to give you basic ideas about robot control and modeling. All right, we didn't finish the lecture on Wednesday, so I'm going to pick up from where we left off, which was after the nonlinearity. It's basically motion control. So I also like to call this set point tracking. Because so if you think about, when we talk about robot control, we usually want to control the position of the end effector, right? Because we have a task that we need to do. We need to reach to a position, and we want to control and make sure that we get there. Now, that is for position control. You remember like velocity, kinematics, and all of that, right? So we sometimes need to control the velocity, but once we have the position, velocity is just the rate of change of that. So when we solve our dynamic equation or equation of motion, we solve it for position, then we can drive the velocity from it. We can control the velocity. Now, we understand why we have to control the position, right? So I want to know what input will take me there, what change of angles will result in ending the end effector there. Can you think of an application of velocity control here? Let's pick and place. How would velocity control impact? Like, how do you see velocity control here? Think about it. Does my question is it clear what I'm asking? Because position is control is where this is, I want to grab it. So I need to know XYZ of it, and then solve the inverse kinematic, send my joint to the angle needed, and check if the angle actually went there. So controlling that, and then go grab it, right? Get there and then use the grabber and grab it. Why would we need also kind of velocity control? Why would we need that? How do you see that application? Yes. Yes. So you don't want to like hit, right? So you want to slow down when you get there. So there, you need to also have a velocity controller. Right now, we just talk about position control, but have in mind that when you design your controller, you have to think about the velocity aspect, which is the rate of change of this position. Thank you. Good. All right. So now let's say our robot has to follow the path to solve that donut and to our robot, right? We pick points and it has to go there. Now we have to control it to go through all of those. Or pick a point and we want our robot to get there and we have a path because we know that there are obstacles in the area and we don't want to hit that. So we choose the best path to go there. So it's path time. Now, let's say your robot has to follow a path. With the knowledge we have, how do we approach it? The path is usually an equation, right? So the curvature or something. How do we use the knowledge we have, like right now, what we learn from feedback control and the position control to solve that problem?
Knowing what your boundaries are, sure you have some sort of movement which excludes those areas.
Which is following all the points on the path we define for the robot, right? Now, your path will change with respect to how the obstacles are arranged. So you want to design a controller that can navigate through this building, right? So it needs to find the best path and then follow it. So right now, we're talking about following that path. There are algorithms that we said, for example, RRT will tell you which path is the best to go follow. Then you have to actually follow the right path. If you think about position control, position function, all the paths are made of points. So if you think about it as a problem of I have to get to each point on that path, you will have a vector of points, right? That at each time your robot has to get to that point. So it becomes a discrete problem. You just need to reach that point. That then once you're there, that's your initial position, and you need to go to the next one and the next one. So you can follow. So trajectory planning with trajectory control is basically set point trash. You pick a point, you go there, and then you pick the next one. That becomes an automated process, right? You can define for loop, like very easily put, and then the robot can follow that. If the path or the points change, doesn't matter. Your control can still do that, right? Does that make sense? So if you're boiling down a very difficult problem to something very simple that we could use using what we learned, becomes there's a point, you need to find the inverse kinematic of that, making sure that how many solutions exist, so your robot doesn't go like in this position and it's following to this position to this position. It's being consistent also, like you're considering the tangent of the path that you're building in small increments, right? So your robot doesn't break. So when we say motion control, that's what we're talking about. Boiling down just to the point, like set point control. So for our position control, for the control, we defined a PD controller earlier, right? If we wanted to add PID controller, we can just simply add the I term. We already know how it looks like, and we can simply add it to our controller if it was needed. Most cases, you don't need all three terms to control. PD usually actually helps. So it's either your control is P controller or PD controller. So the equation that we came up with, and we're solving it for unit mass, so we can apply it to any link in the robot. So our F prime, the controller input, the outside force that we're trying to control robot with, is negative KV, or you can say KD prime, which is later on will be divided by M, right? The mass of the object, the link, X dot minus KP prime x minus x desired. Here we are trying to control the positions. I'm looking at the difference in the position. If you had some difference, if you had a desired velocity, it will show up the x dot bar, right? So I'm assuming that I don't have x dot desired, I'm just focusing on controlling the position. That's why there's no x dot desired. But if your problem told you there is an x dot desired, just simply the x dot minus x dot desired. So you're looking at that difference, right? And multiplying it by a coefficient. So for your closed loop, if you have a simply, if you think about a mass spring damper, which we will model a lot of our application with mass spring damper. If it is just a prismatic, let's just focus on the simple problem of the prismatic. Is x double dot plus k prime v. It's 1 because we are solving it for a unit vector. X dot plus k p prime x minus x desired. Now, you have two ways of solving these. One is using well, I'm talking about if you're using MATLAB, let me correct myself. If you're using MATLAB, you have two ways of going. One is scripting, writing the code to solve it. One is using Simulink to model the system and let the solver solve it. It does the same thing. It's just like dragging boxes and setting up the system and letting it solve. How many of you have used Simulink? Raise your hand. Okay, good. If you haven't, if you're gonna go in the world of modeling, it's a good skill to have. If not, don't worry about it. Like what you know on MATLAB is enough because basically Simulink does the same thing with more sophisticated. So if I want to show this, if I want to model it in Simulink or show the block diagram of that, I have a system, right? And I want to show my control that I'm adding to the system. Your controller is before your system, right? The part that we get, so here would be my x desired, let's say x desired. And I want to implement my controller into this. Show the block diagram of it. If I move this guy a little bit down over here. All right. So this is my output, right? That is, let's say, x, the state that I'm measuring or I'm seeing after it went through the model. So this is my x. X desired minus my x will give me the error, right? Now, which one of those blocks have to go right here in the top signal? Meaning that which one of the elements or parameters of your PID controller or PD controller will be multiplied by the error itself? KP component, right? So this is your KP. So in Simulink, you can just create a gain. KP is a gain, it's a number, right? So I'm assigning a gain, and I'm saying that whatever error you read, apply to that. Now, if you decide that you only want to use a P controller, which is totally fine, depending on your system, that's all you will get. Like you'll have KP as your controller, goes to your system, and then you see the error, and at some point you reach the value that always can control your system to the X desired that you want. Right? Now, if we say that this is not enough, we need to add another element. You can use, let's say, our KD, like PD controller. Now, we are moving from time domain to S domain, right? So let's say I have KD here, or KB, however you want to call it. What was KD multiplied by? Was it the error? Was it the error itself? Do you remember the control law? Is differential, right? It's a differential component. So it's dE to dt. So it wasn't E signal itself. In our model, we have E. We don't have dE. You need to trade that. You know how to do that in Simulink or in S domain? How do you do that? What does it mean? Yes. it means that you're adding S block, right? So that is your PD controller. So it has two, so your controller will have two elements in it. It will have a KP multiplied by the error directly, and also KD multiplied by S, which in time domain is D to DT. And then that will go to your system now. Now, if you wanted to add KI or the integral controller, we need to show the integration action, right? So we have KI, then integration in Simulink or in S domain is 1 over S. Well, this is not, this is, and then these are just your, connecting to it, because they all get there. Now, if I wanted PI controller, what should I do? Build this controller for all three items. How can you eliminate one without changing your system? Set your KI to 0. So we build it for our whole PID controller, but we can set our values to 0. But we saw that, oh, for some condition, I see a lot of oscillation in my system. So oscillation means that you're having accumulated error from past, and then you overcorrect it to go up and down, up and down. That's why you have oscillation. To remove the error accumulation, things that happened in the past, we use the integral part. So then you can give a little bit of KI to your system, and then you can get rid of the oscillation. Right? So in no matter where you're using control, you have to have a good understanding of your system and the behavior. Then you can decide which of these factors, these coefficient gets a bigger value or lower value, and which one are the dominant part of it. There is no recipe of if this happened to this. You have to understand it and see and understand what each element does. It works for autonomous robots on the road. It works for robots, for our robots, like manipulated arms, any controller. It's the same concept. Yeah. So to my eye, I taught you control. The part that takes time is practice and using it and seeing it in action. Right? So if you had control, you remember that you had to do a lot of our assignments. Tuning controller, hopefully they did that to you. Yes, I know I do that to you. Then you get an understanding of how changing each of them will impact your control. And remember, we're doing all of this for the set point trajectory tracking, because we want to make sure we land on the point we said we're going to land, so we can go to the next one. Otherwise, what would happen if you have a little bit of error of the position of each point on your curve? You don't get where you want it. You could follow the curvature, but not the position. You could end up somewhere very different, right? Okay, so for trajectory tracking, we can, so if we needed to also control the velocity, then we can add the x dot. I'm just going to write the equation. So your f prime would be x double dot d, because you might want to control the acceleration as well, right? Minus kv prime, x dot minus x dot desire, minus kp dot, x minus x desire. Sorry, you're not controlling the acceleration. When you have rate of change of velocity, you have acceleration in your system. So you want to count for that. That's why you have x double dot d. All of these belong to your controller. Now you have to add this to your system, right? Then you put together another second order system. So your closed loop system, which is your controller and your system, would be x double dot minus x double dot desire, could be 0. Don't change the acceleration. I want to have 0 acceleration, so a constant rate of change of velocity. Plus kv prime, I'm just putting them together, x dot d, plus KP prime X minus X desired equal to 0. So these are all for that one prismatic point that we talked about. So we haven't even gotten into angular velocity yet. Now, my error, I can define if I'm doing position control, the error is X minus X desired. So E position control. Now, you remember we can control the error as well. Like we can look at the dynamic of the error and plot the behavior of our error. We can also write the equation for the error dynamic. For E1M of the error is E double dot plus KV prime E dot plus KP E, which is coming from here. We're defining an error in acceleration, an error in velocity, and error in position. We can define this and look at this instead of solving that every time. We can actually look at this. Once the error is what we wanted, we could use these coefficients and then follow our system. All right, so whenever you work with feedback controllers, you might hear feed forward and feedback controller. Does anybody know what feed forward means? Like what's that? How do we use that in control? We know what feedback is, right? We look at our solution, we see where we want it to be, the difference, we feed it to the system. So we look at the feedback and control system. What does feed forward mean? If you heard about it, you know. If not, you won't know. Who have heard about feedback? Feed forward. What does feed forward mean? So one application of feed forward is when you don't have a feedback in your system, but you know how your system should behave, you do that. But you can have a feed forward and feedback in your system. You could have all the sensor, but you could still use feed forward. The good thing about feed forward is that it's part of your input and it will send your system to the vicinity of where you think it should go. And then from there you control the system. So for example, underwater drones, robots, if they have gravity and buoyancy engine, meaning that like that my application in my PhD, so there was no thrust or nothing, you had to take water in, becomes heavier, just goes down. All right, and then you have to reach a set point and then come back up, so it had a zigzag motion. Now the thing is, you can carry so much battery and power in those. If you're trying to control the system the whole way, you're constantly consuming because you're constantly trying to control your actuator, right? Your pump. What if I knew to reach to 30 meters underwater, I need to add this much weight? So I'm going to feed forward and say, you know what? Take 100 milligrams of water. That will take it to 95-ish meters. I'm feeding forward the control command to it. Once it reaches to that stability of wherever it's close to 100 meters, then feedback kicks in. It's like, oh, we are at 95, we need to go 5 more. Then I'm full power actually using this. The power consumption will decrease by a lot. So one reason if you don't have a sensor, one reason is that you can save on power consumption and also calculation power, processing power. Right? Sometimes you're fighting a disturbance from the environment. You know that you have to give a constant value, like when you have this in dynamics, right? So you know that you need this much to account for it, then you can feed it forward. So a lot of time we use feed forward, feedback together. And very, very interesting. And the system is very simple. Feed forward is usually a fixed value you add to it. Right? I don't know if your book talked about it, but I think it's very useful in control theory or when you're controlling a system to think about feed forward. Can we just use feedback for like the whole journey of my glider goes up and down? Yes, I can, but I probably need to add like another 15 milliamp to my battery power. More expensive, more weight, more space, you know. So again, all comes down to you as engineer, how do you think about control? Okay. Any questions so far? No? Other things that you would come across in control is disturbance rejection. What do you understand of this term disturbance rejection? What does it mean for you in terms of control? No? No? Yes? If you have a noise or something from the environment applying to your system, you need to reject that, right? Meaning that you have to account for it. So let's say, remember like me driving and then I hit the speed bump and my dog goes to the window, right? So those happen from the environment. If I'm on cruise control, the car will eventually catch up with it. So you have to see the disturbance control on it. So you take less time to reach to the desired value. So you can see your disturbance control added to your control input. So if you remember, we first started with linearizing your controller and defining your control input. Then we said, if you have nonlinearity, add it as a fixed part to the system. Study the nonlinearity separately. If you have disturbance, you have to study separately, see what is the impact on your system and add it to your control input. That's basically what this rejection is. I've already seen what the impact is. I'm gonna add it to my control input. So I see you. I see you. I know you're there, and I'm equipped with in my control input. So if you have some nonlinearity, if you have some disturbance, you can say that your controller is some m f prime. F prime is your control input for linear system of unit mass times m is for your system plus some function that can include all of those extra stuff. If you're modeling and simulating, it will be different branches that has a block for disturbance, has a block for nonlinearity, and they all will be feeding the system. You're still focusing on your system itself as a linear system, right? This just makes it easier, but we are making a lot of assumptions separating them because they might not be independent, but we are assuming they are. So when you have disturbance, when you have nonlinearity in your system, you have to consider that what you get might not be the actual behavior of your system. It would be close enough if you tuned it properly. So you always have to run the experiment for the final tuning of your coefficients. So if we add all of those to our closed loop system and looking at the error, E double dot plus KV prime E dot plus KP prime E would be some F disturbance divided by M because we are using KV prime, so it's for a unit vector. Now, if I have a steady state error, steady state means that the error does not change over time, right? We reach to a value that is not changing. So there is no change of velocity, there is no change of acceleration. So that equation can be simplified to Kp prime error F disturbance divided by M. So I can say that my error would be my F disturbance divided by M Kp prime. By the way, this is your Kp, right? It showed up again. So This is your closed loop error. Your disturbance divided by your frequency. That's what error you will get for that system in the steady state. So if you have a disturbance, your system reaches steady state error. You want to know what the error would be. Why? Because you want to see if this error is good enough. Can I like ignore it? So you can use that. Like, what is my disturbance? What is it that KP that directly control it with? If you divide them, then you can't guess. So guesstimate or estimate. So you can reverse engineer this. 0.001 is good enough. If I know what my F disturbance is, I'm going to pick a KP to ensure that I reach the error. So you see that everywhere I talk or attack, we end up to the same thing. That we need to drive the error to 0 or something that we are happy with and we can ignore. And it ends up, if you're using PID controller, it ends up being how we tune these three values, KP. This is all about controlling the robot, really. There isn't much left, like there's not much more into it. For this example, this is basically the same thing. I'm just giving you the annotated version. I will give you the annotated version. I will be the same thing. This is just plotted, and I already talked about the equation. So don't worry about that. You can just read it. Now, if I wanted to add the integral part, I just bring the Ki to the equation. So then I will have P, I, and D controller. So it's a full three-factor controller. So your equation, your controller becomes x double dot desire, KV prime, x dot minus x dot desire, KP prime, x minus x of D, minus Ki, the integral of the error, which is the position error, right? So this becomes your control law. And for your closed loop system, if we write based on our error, is E double dot plus KV prime, E dot plus KP prime E plus KI prime E dt equal to, now if you also have disturbance, because we always want to reject disturbance, right? So we want to see if there was a disturbance, so we can fight it. Reject it. So it's F disturbance divided by M. So you see that I'm writing a general control law, right? Now, what if I didn't have disturbance? F is 0 divided by M, it's 0, nothing happened. I have my control law for non-disturbance. What if I just wanted to use PD? Well, I'm going to put Ki equal to 0. So it's good that you have the whole controller, and then you can set whatever you want. Now, if you had nonlinearity, you'll add it here as a fixed value. If you didn't have it, you put it equal to 0, it's there. Okay. So these are all about like PID controller. Doesn't matter what application you have. You can use the same concept and it's the same control law. Question? Okay. All right. Well, that was one last class. But so the things that I brought for today is just an example. We already went through all of those, so we don't have to do that. Now, how to drive the equation for if you wanted to control a single arm robot, because you have to do it for double ring for your homework, right? Where do we start? Starting with writing the equation of motion. Okay. So do we know the equation of motion of a single link manipulator? When I say single link, what do I mean is, so there is an R joint and there is a link connected to it. This link has, let's say, length of L1. The center of mass we can define as R1. We know that there will be some gravitational, so I'm going to write gravitational force here applied to the system, right? And then I need to write the equation of motion. That's all that happens in my system. We have already solved this before, correct? So I'm gonna just write the equation. M1 R1 squared plus I1, so we have inertia, theta double dot 1, plus M1G cosine of theta 1 equal to some tau 1. So tau is a generalized torque or force. Depending on what your system is, if you have prismatic joint, it will be a force. If you have revolution, you have a torque, right? Because if I wanted to control this externally, have to force it, I have to use a torque. All right, so this is my equation of motion, but what am I solving for? What am I trying to do here? I want to control the position of this robot, the angle, right? Because I want to reach the specific angle. So it's the inverse dynamic. We got to rearrange this to get, because we want to see what theta double dot is. Negative M1G cosine of theta 1 plus tau 1, if we had it, divide by M1 R1 squared plus I1. So this is the equation that I need to solve. You can use ODE, right? Convert it to first order system. If you know how to use simile, you can also have the blocks and then solve using simile. It will give you what? What would be the output of whatever you use to solve? Yes, just say louder. Huh? Yes, the state. Yes, we always want to control the state of the system. But for this system, what is it that you're controlling? So you put this in MATLAB, you write all the code, and then it plots something. What is it that you're plotting? I will tell you, it's against time. What is your y-axis? Theta 1, the angle is the state, but you can't just say state. Anything could be the state. How hot it is the state, right? Depending on what you're controlling. So really, you want to be clear and objective, you're engineers. So here, if I solve this, and I plot it, because MATLAB does all of that for you. Someone wrote the code. You don't know what is in that OD45. It will plot it for you. But you need to be able to interpret that. Hence, when you give me your homework back, all the axes have to be labeled. If you have two graphs in one axis, what do you call it? Graph. In one plane, you have to color code it. What does the blue mean? What does the red mean? All right. If you just plot something and send it to me, it doesn't have any value to me because you didn't write the OD45. Someone else just used it. But the minimum is you understood what's the output. Okay. If it doesn't even say in your rubric, I will look at it. And if it's not there, you're not getting the whole point. All right. So I will solve this and it will give me theta 1, which is the position, the angle, change of the angle, right? So now if we want to design a PD controller, let's say this is my robot arm. I want it to go to 45 degrees, the angle. So I'm gonna pick a point, 45, this has to go there, right? So I can just send it for 5. One way is, okay, send this, like use time, run this for 2 seconds, see where it lands, right? We can do that, but that's not a very smart way because you have to keep plotting to find what is the golden time. You could design a PD controller. You're designing to control the position. I want you to get to 45. Now, how do we design the PD controller for this case? Do we know the control law? Yes. What do we need to do? Yes. No. It's the input, which is the force from the external, right? You're controlling. So this how you can replace it by your input, your controller, and you already know the control law. How does it look like? Then we have our equations. We have our equation, the two sides. We can again solve this, but now we have our KP and KD, which you don't know what they are. Depending on the requirement, we're going to start with this to guess, right? We went through that like a very long conversation. I hope I'll all forget that. It's not step input. So here's the thing, is when you say control input, if you wanted to give a fixed value, like if you're using P controller and you figured out what is your KD. You already tuned it, then you know it's a fixed value, then you're not changing. Then yes, you can use that. So that's for when you tune everything and you want to see the result, right? So every time you tune, you can say, this is the tuned one. Then you can use a step function and then see how it looks. No, it is not. Draw another one and look at it, right? So that's why you can use a step for it, because you can assume this was the tuned one. Then it's like, no, there's some error, I'm gonna move that until you get to what you want. Now, how to incorporate, that's the $1 million question. So tau 1 has to be negative Kp, right? Theta 1 minus some theta desired, whatever that angle is, minus Kv or Kd, whichever you like better, Kd, theta dot 1. What is theta dot 1? D theta 1 dt, right? So we already had this equation. We just wrote what tau is. You replace all of that, all of those are fixed values. This is a fixed value, right? This is a fixed value desired. This is a fixed value. And here, if you have theta 1, you just get if it's discrete, it's theta 2 minus theta 1 divided by time, right? So you already have that. So we are solving for theta 1. So and then here you have theta 1. So we are solving this for theta 1. Now, your theta d is what? Your reference or set point, right? So your set point tracking, you're controlling the point that is desired. Now, if you want to track a curve that is a circle, you're going to start from, go to 1, go to 2 in a for loop, all the way back, and you have the ability to stop it at any point because it's controlled. Now, single arm is not very difficult. I'm assuming it's 2 lanes. And there are so many different ways of that moving, right? So for your homework, the homework itself, you just have to solve. Then plot what is theta 1, what is theta 2. There are 10 extra points that goes to the animation, up to 6 points. I'm gonna say up to because you could just plot it and don't like change the color or change the axis. So I'll give you some point for doing it, but you don't get all of it. Like if you do proper job, you get all 6 points. Then there's 4.4. Now let's change condition, initial condition where you start the motion and show me how you change it. Does it impact? Basically, I want to see if you understood initial condition, how initial condition will change the robot. You asked if it has to be inverted pendulum or hanging pendulum. Hanging pendulum is easy because you start from position, you let it go, you saw what happened. Just went random, right? Inverted pendulum, if you start here, at one point it's stable and then it will fall. If you want to keep it there stable, you need a controller to always stay here. That's a very difficult, in reality, that's a difficult. So have you seen cart in inverted pendulum? The cart moves, gets acceleration, velocity, but the pendulum has to stay. So at any time, the controller has to keep it the same orientation. So for the purpose of this homework, you can use hanging pendulum. Pretty easy, just the same problem. But you'll have theta 1 and theta 2. Good. I don't know if in your homework I told you what is the condition I want you to solve for. Did I say it? Okay, good. Then you know what it is.